Figure 13.2, divide by zero with exception handling. In this example, we're going to show you how to make your programs more robust by enhancing them with exception handling to trap runtime problems as they occur. Now, for the purpose of this example, that will enable us to allow the user to re-enter their input and hopefully produce a valid division. So as we take a look at this example, we want to first show you the syntax that we've added for exception handling, and then we want to talk about the flow of control both for valid executions and for cases where exceptions occur, so that you can understand how the flow of control works in the so-called exception handling mechanism. Now, as we take a look at our class divide by zero with exception handling, you'll see that we once again start with the quotient method, which is a static method, so main can call it directly. And you'll notice one change from the last example, which is this new clause called the throws clause, where we say throws arithmetic exception. This serves as a form of documentation to the client code, in our case main, indicating that there is the possibility that the body of this method will throw an arithmetic exception. So if the denominator is 0, when I get to line 12, this division will fail and the Java programming language itself will throw an arithmetic exception back to where the quotient method got called. Now let's talk about the main method and see where that is. So in main, once again, we're going to have a scanner to read from the user at the command line. We're also going to have a continue loop Boolean variable which is set to true, and that's going to help us control this do while loop in main, which will continue to iterate as long as continue loop is true, and which will terminate as soon as it becomes false. Now the key new feature in the example is this try catch sequence inside of the do while loop in main, and starts with the try block, as it's called, which is a block of code enclosed in curly braces and preceded by the try keyword. Inside of a try block, you place any code that might cause a problem, as well as any code that you don't want to execute if such a problem occurs. So let's talk about that for a moment. At lines 24 and 25, we prompt the user to enter an integer and we read the integer in. Now, we showed you in the last program that at line 25 that could cause a problem. In particular, it could cause an input mismatch exception if the user, for example, types the string hello instead of an actual integer value. So this is a potential problem point in our code. That's why we've wrapped it in a try block. Also at lines 26 and 27, we prompt the user to enter another integer and to read that value. And just like line 25, line 27 may also cause an input mismatch exception, which is why we've enclosed it in a try block. Now at line 29, we call the quotient method from up above, and we know the quotient method is going to attempt a division, and if the denominator value is 0, we know that division is going to fail from showing you the last application, the last program. So this line also might cause a problem. Now, if we can't perform the division, it really doesn't make sense to display the results because we don't have any results. So we've included in line 30 and 31 the printf statement that's going to display the results, and that's inside the try block so that it doesn't get executed if the problem occurs. And the reason it won't get executed is because try blocks terminate as soon as a problem occurs. So if line 25 causes a problem, lines 26 through 32 will be skipped. If line 27 causes a problem, lines 29 through 32 will be skipped. And if line 29 causes a problem, lines 30 through 32 will be skipped in that case. And you would jump immediately to the end of the try block, and at that point you would start looking for a quote-unquote matching catch handler, where the definition of matching means that the type of the exception that was thrown matches the type that was caught, and that means has an is-a relationship with the type being caught. So the type being caught could be the exact same type or a superclass type of the exception that was thrown. All right, so the try block is again for anything that might cause problems and anything you don't want to execute if a problem occurs. Now, a catch block starts with the catch keyword and a set of parentheses wrapped around the so-called exception parameter, which consists of the exception type name and a variable name, a parameter name, into which the exception handling mechanism will place the exception object when it occurs and we have a match. So if the type of exception that occurs is an input mismatch exception, the exception object would be assigned to this variable, and at line 36 and 7 we would then print the two-string representation of that variable. Then at line 38 we would read in any remaining input that has not been read yet and throw it away. And at line 39 and 40 we would tell the user that they have to enter integers and to try again. If we reach the closing curly brace of a catch because of an exception, then the exception is considered to have been handled. All other catches following the corresponding try block are ignored, and we simply move on to the next valid statement after the try-catch sequence, which for us is going to be to test the condition of our do-while loop and then possibly go back up to the top of the loop. If an arithmetic exception occurs at line 29, we would actually skip the exception handler at lines 34 through 41 and take a look at this other exception handler which catches arithmetic exceptions. So if we get an arithmetic exception, the object will be assigned to this variable. We will print the string representation of the object, and we will print out that 0 is an invalid denominator and that the user should try again. Right, so now that we've looked at the basic syntax of this try-catch sequence, let's talk about the flow of control through this example. We're going to execute the program 3 times, first with a valid flow of control for valid numbers that are non-zero for the denominator. Then we're going to look at what happens when we get an input mismatch exception, and then what happens when we get an arithmetic exception. So for this purpose, we're going to go to a command prompt to run the program. And I'm going to go ahead and execute it and type a couple of valid integers. So let's say I type 107 like we did in the first program. We get a valid integer result. So let's talk about the flow in this case. When main executes, we create a scanner to do our input, and we create the Boolean variable continue loop and set it to true. We then flow sequentially into our do while loop, and we try to execute the highlighted code. At line 24 and 25, we prompt the user to enter a numerator, and we read that value in. And at lines 26 and 27, we prompt again and read the next integer value. At line 29, we call the quotient method, which brings us back up to the top of our class here, where we receive the 100 as the numerator and 7 as the denominator. We perform the calculation and return the result back to the caller. That places the result into the variable result at line 29. We display the results, and we set continue loop to false because we had a valid or successful execution. We then reach the closing curly brace of the try block. That indicates that we successfully tried everything in the try block, and therefore there is no need to execute any of the catch handlers because nothing went wrong. So in that case, all of this highlighted code would be skipped. We'd proceed immediately to the while condition in the do while loop. We'd see that continue loop is now false, and the program will then terminate. Now let's take a look at what happens when we have an input mismatch exception. So we're going to run the program again, and this time I'm going to type 100 for the numerator and hello for the denominator. Now in this case, we see that we got an input mismatch exception. We also saw our message saying that you must enter integers, please try again, and you'll notice that the program has prompted me again, and rather than just terminating prematurely, I am now able to go ahead and type a valid set of values and show you a valid division. So let's talk about that flow of control. So once again, we flow into main, we create a scanner and this Boolean variable continue loop, and then we flow sequentially into our do while loop and sequentially into our try block. In the first case, we prompted the user for an integer, and I typed 100, which was a valid value to be assigned to the numerator. Then we prompted the user for another integer, and in this case, I typed the string hello, which is not a valid integer. So line 27 then threw an input mismatch exception, at which point the try block terminated, and we jumped immediately to line 34. Any of the local variables in this try block went away, so they are not accessible to us outside of that block. At line 34, we see that the type of the exception that was thrown was input mismatch exception, and the type being caught is also input mismatch exception. So we have a match. The exception object gets assigned to this variable, And then at line 36 and 37, we print the string representation of the exception object, which, if you take a look at our output, consists of the complete name of the class that occurred, and if there is an error message as well, that would appear to the right of the class name. Then at line 38, we read in any remaining input, if there is any, and we throw it away. And then at line 39 and 40, we print out that the user should enter two integers and try again, and you can see this part of the output here as well. Now, once we reach the closing curly brace of the catch, we've handled that exception. The exception object gets marked for garbage collection, and we simply skip any remaining catch handlers and move to the first statement after the try-catch sequence. In our case, that's the condition in the do-while loop. This time, continue loop would not have been set to false because we skipped all of the code in the second half of the try block. So we'll come back around to the top and we will try everything again, which is why we were able to type two valid integers and get a valid result. All right, so now let's talk about what happens when we get an arithmetic exception. So we're going to run the program again here, this time typing a numerator and 0 for the denominator. And we immediately see that we got an arithmetic exception where we were trying to divide by 0. We told the user it was an invalid denominator and that they should try again. And again, notice that the program has not terminated. We've made it more robust by trapping this problem, and now we can type in a valid set of values and get a valid result. And now let's take a look at the code in main once again to see how we flow in this arithmetic exception case. So again, in main, we create a scanner, create the continue loop variable, and flow sequentially into the do, loop, and the try block. We prompted the user for an integer and read it in. We prompted the user for another integer and read it in. And we had two valid integers in which the denominator was initially 0. When we got to line 29 and called the quotient method, that caused us to execute this return statement in the quotient method, and when you divide by 0 in integer arithmetic, you get an arithmetic exception. If there were any other code that could be executed after line 12 here, it would be ignored. The exception gets returned to the point at which this method was called, which is line 29. The system recognizes that line 29 is inside of a try block and terminates the try block immediately, thus skipping lines 30 through 32 and getting us to line 34. Now in this case, the type of the exception thrown was an arithmetic exception, which is not a match with input mismatch exception. It's not the exact same type, and arithmetic exception is not a subtype of input mismatch exception. So this catch handler is skipped entirely, and we jump to line 42, where we do find a matching catch. So the exception object gets assigned to this arithmetic exception variable. We print out the string representation of the exception object, and we print out a message telling the user what they need to do to continue. We then hit the closing curly brace of the catch. That terminates the exception handling process. The arithmetic exception object is marked for garbage collection, and we continue with the next valid statement after the try-catch sequence, which in this case we see that continue loop is still true, so we come back around and try again, and you saw that I was able to type two valid integers and get a valid result. So this example nicely illustrates how we can make the previous example more robust. It introduces the syntax of the try-catch sequence. In subsequent examples, we'll introduce other syntax that we have not discussed as yet. In particular, there's also something called the finally block that we can use at the end of a try-catch sequence, and it's a block of code that will always get executed. Now, one last thing before we move on to the next example, which is why is this mechanism of handling exceptions a nice way to go? Well, if you think about some of the past programming languages that you might have used that did not have exception handling, it wasn't uncommon to do things like have a global variable that represented whether or not an error occurred. You would set that variable perhaps to 0 before you call the function. You would then call the function. Then you'd have an if statement that checked to see whether or not the function caused a problem by looking at that global variable to see if the function itself changed the value of that global variable. If an exception occurred or if a problem occurred, you would then have code to execute because of that problem, and if not, you would then move on to try the next thing that you wanted to do. And what this did is it caused you to intermix a lot of your error processing code in line with the basic logic of your program, thus cluttering the logic and making it harder to understand, debug, modify, and maintain. The nice thing about the try block is that we only put in there the things we wish to get done, and only if something goes wrong do we ever look at the error handling code. This actually can make your programs even more efficient because of the fact that you don't have to continually keep testing to see if a problem occurred. The system takes care of that for you. So now we're going to move ahead into other examples and take a look at the rest of the exception mechanism.
Looking to advance your career by acquiring new skills? Tired of expensive off-site training programs? Wish you could learn from the best instructors in the industry? Look no further than live lessons. Self-paced, personal video instruction by the world's leading technology publishers. Each live lesson comes with a DVD featuring 3 to 4 hours of instructor-led classroom training, sample program code that allows you to work along with your personal instructor, and an example-rich study guide. Live lessons allow you to watch the entire course from start to finish, or navigate directly to any of the individual lessons. You'll literally watch over the shoulder of your instructor as he shows you how to build state-of-the-art applications. Live lessons, the power of the world's leading technology experts at your fingertips. To learn more, visit mylivelessons.com today.